let's put everything we know together about uniqueness of solutions for higher order homogeneous linear differential equations. Let's put all of it together with an example. So here we have a differential equation, y double prime plus 6y prime plus 9y equals 0. That is linear and homogeneous. And it has solutions e to the minus 3x and x times e to the minus 3x. So for now, it's going to be my secret how I came up with these solutions. We will discuss that later. But for now, let's just answer these questions. Are these solutions linearly independent? And if so, let's find the solution that satisfies this initial value problem and comment on the uniqueness of the solutions. So let's look at part A. Are these solutions linearly independent? So just looking at them intuitively, it kind of seems like it because they seem sufficiently different, right? I don't know how you could multiply one by a constant to get the other. But remember, the right way to check, or the most general way to check if these are linearly independent, is to calculate their Wronskian. So let's find the determinant of, so this one's going to be 2 by 2, fortunately. 3 by 3 gets a bit messy. But for 2 by 2 determinant, for the Wronskian, we get the functions themselves on the first row. So e to the minus 3x and x e to the minus 3x. And then the derivatives on the second row, so minus 3e to the minus 3x. And now we have to do the product rule. If you do that and simplify a little bit, you're going to get something like minus 3x plus 1 times e to the minus 3x. So you can work that out. And then now we need to calculate this determinant. So remember, it's the first diagonal with a plus, and then the second diagonal product with a minus. So we get e to the minus 3x times minus 3x plus 1 times e to the minus 3x, x up there, minus, and then we do the other product, x e to the minus 3x times minus 3 e to the minus 3x. Okay, so let's simplify this. Here we have some exponentials we can put together. This is e to the minus 6x times minus 3x plus 1 minus, let's see, here we have exponentials we can put together again. So e to the minus 6x, and then there's an x, and then there's also this minus sign here, which makes this a plus. Oh, and I missed my 3 right there. There we go. So this is minus, distributing this exponential, this is minus 3x e to the minus 6x plus e to the minus 6x plus 3e to the minus 6x, e to the minus 6x times x, there we go. And these exponential times x terms, those all cancel, and we're just left with e to the minus 6x. And remember, we want to know, when is this 0? Well, this is never 0. So this is non-zero for all x. And remember, a non-zero Wronskian means that our collection of solutions, e to the minus 3x and x e to the minus 3x, is linearly independent. Okay, now if you look at our original differential equation, since it has constant coefficients, the coefficient functions are all continuous, and the leading coefficient function, the 1 right here, is never 0, and so our uniqueness theorem applies. So since we have a linearly independent collection of 2 solutions for a second order equation, all solutions to the differential equation will be a combination of these 2 that we already started with. Okay. When you have a collection of solutions like this, e to the minus 3x, comma, x e to the minus 3x, when you have a collection of solutions that's linearly independent and all solutions are a combination of those two, then this collection of solutions is called a fundamental set. Fundamental set of solutions. So what we're really looking for is a fundamental set of solutions, because if we have a fundamental set of solutions, then every solution is a combination of these. So again, for a fundamental set of solutions, we need two things. We need unique solutions for the differential equation, right? We have to be able to apply that uniqueness theorem, and we have to have a linearly independent set of n solutions. And then you know you have a fundamental set. For this equation, n is 2 because it's second order, and we have two equations. All right, good. So this is a fundamental set. It's a linearly independent set of solutions. So part B was find a solution to this initial value problem and comment on its uniqueness. Well, because we can apply that uniqueness theorem, we already know there's going to be a unique solution to this initial value problem. And because we found a fundamental set, we know that the unique solution to this initial value problem will be among the combinations of these two solutions, y1 and y2. So all we have to do is find the combination of y1 and y2 that satisfy these initial conditions. So y of 0 is supposed to be 3, and y prime of 0 is supposed to be 0. So these are our initial conditions. Let me just check that I copied those right. Yes. Okay. And right, we know that every solution is going to look like some combination of our fundamental set. So some constant c1 times e to the minus 3x plus some other constant c2 times x e to the minus 3x. So we can use our initial conditions together with this general form for a solution. So plugging in x equals 0, we get c1 plus 0, it looks like, so just c1. So now we know c1. And then taking a derivative, we have to calculate a derivative. So we get minus 3c1 e to the minus 3x plus c2 times minus 3x plus 1 times e to the minus 3x. Okay, so putting that all together, it looks like we can factor out an e to the minus 3x. We're going to get e to the minus 3x times minus 3c1 minus 3c2x plus c2. Okay, so now we can plug x equals 0 into that derivative. So we get out in front, we get a 1 times minus 3 times c1, but we know c1 is 3, minus 3 times c2 times 0, so that term goes away, plus c2. So 0 equals minus 9 plus c2, so c2 is 9. All right, so the solution that we're looking for is c1, which is 3, times y1, which is e to the minus 3x, plus c2, which is 9, times y2, which is x e to the minus 3x. And so this is the unique solution to that initial value problem, and it is a combination of the two solutions in our fundamental set.